Next set of lectures will be on finite difference method for solving PDEs. Okay, so we discussed spectral method, which converted PDEs to ODEs. Okay. Each Fourier mode had a ODE, but the finite difference scheme also will convert PDEs to ODEs, but at each real space points. Okay, or discretized real space points. Okay, so let's see. We'll see how to do it. So these are PDE, no? So this is a equation in time, and okay, so this equation depends on, it has partial derivative in time and partial derivative in x or x squared. Well, I mean second derivative in x. Okay, so phi is function of x in t, and we stick to 1D for time being. Okay, now this equation was exactly the same what I wrote in the first slide for spectral method, but let's see what we do in Fourier in real space. Okay, so first step in finite difference scheme is to discretize space. Okay, so in 1D, no, so 1D, let's imagine that my field is 0 at both ends, so it's called vanishing boundary condition. Okay, so the field is 0 at both ends. Okay, now I just take typically endpoints. Okay, so I'm not measuring the function at each point, but measuring at discrete set of points. So phi 0, phi 1, phi 2, phi da 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 da, phi n minus 1. So they're endpoints, but we know by the boundary condition that it is 0 at the ends. Okay, so you'll be given a boundary condition. Yes, and okay, imagine that it's vanishing, then we need to set it to 0. Sometimes we get periodic boundary condition, like Fourier transform, we remember we had a periodic boundary condition. And for that case, phi 0 and phi n are same. Okay, so I go from phi 0, phi 1, phi 2, da 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 da. I come back to phi n minus 1 and phi n. Okay, so here I save the values at phi 0 to phi n minus 1. So there are n points again. Okay, and we need to solve this fields at those points. Remember, this phi n is the same as phi 0, so we don't save phi capital N. We do not save this. And the basic idea for this stuff is, so we have the discrete values now. So, you have that like that. So, we write down phi at that point. So it's going to be phi it d by dt. Now, I already have chosen I as the index, no? So x is not a continuous variable anymore. So this becomes a ODE, right? Because phi I d by dt. Okay. So once we have x is continuous variable, then we have PDE. As soon as x is discrete, then we have ODE. And the right hand side, we compute at that I. Okay, of course, this involves derivatives. If the derivative, then I have to compute at xi, but I need to use values to the left and to the right and so on. But the derivatives can be computed by second order scheme, third order scheme, fourth order scheme. So we can compute that and substitute it. I mean, basically get fi. Okay. Now, this is a differential equation, ordinary differential equation at site I. Now we have n points. Okay, so we'll have n differential equation. Of course, if the boundary condition is fixed, if it's a vanishing boundary condition, then we do not time step. It remains 0, so we don't want to time step that part. Okay, so all the free points where the phi is evolving, we get set of ODEs and we need to solve it. Okay, that's the basic idea. In fact, in some sense, it's much simpler than the spectral method. But remember that spectral method is more accurate. We did, in fact, we had a detailed discussion to show that the derivatives are more accurate in spectral method compared to finite difference scheme. Okay, so but it's easy to set it up, finite difference scheme. And once we have the ODE, then I can solve it. For every point, I just solve phi n plus 1 is phi n plus delta t times fi. This is Euler forward. You can also do Euler implicit and so on. This should be at n. Okay, and okay. Now, so I just make a sketch. So we have the time is going upward in this sketch only. So at t equals 0, we have the values of the function at all the grid points given here, phi I 0, phi 1, phi 1 at 0, phi 2 at 0, and so on. So remember I had this index is a time index. Okay, superscript. And the subscript, let's say 2. So these are space index. Okay, so this is at second grid point or third grid point. Okay, in Python we have start with 0, the third grid point. And from here I go to phi 1 at 2, and then I go to phi 2 at 2. So these are time is increasing here to here. And that's it. So we can solve it by this scheme. But now let's see what are the complications which arise in finite difference scheme. Okay, so PDEs we solve are same ones we did for spectral method. Okay, identical. But we'll contrast which is more accurate and what complications come in finite difference. So I'll quickly show you the issues involved. So diffusion equation, we saw this before. Phi partial t is kappa second derivative of phi with x. Okay, now we'll use central difference scheme to compute the derivative in x. Okay, so this term, so remember I had like this. And for this example, I'm using periodic boundary condition. So phi it at time t, and sorry, d by dt of phi I. Okay, so we choose the site I. Now the double derivative with x will be involving 3 points, right? I minus 1, I plus 1. This is real space point. Okay, so is I. So phi I plus 1. So the double derivative phi I plus 1 minus 2 phi I plus phi I minus 1 divided by h squared. Okay, so this is what is the second derivative, okay? And multiply with kappa. Okay, so right hand side is also set. Now this is the equation, and which we get is OD. Okay, now we can easily solve it using let's say Euler forward. So this is at time t plus time index n plus 1. Okay, the phi n plus 1 is phi n, and the right hand side computed at n. So this is phi. So all of this at n. Okay. Now we know this. When I time advance, I know the values at phi n. I can get ahead. Okay. So given initial condition, which is given in the real space point at t equal to 0, I can just time advance. Okay. Now, so what about stability? So we need to first figure out what about stability. The first thing is stability. Accuracy, I didn't say much for PDEs, but stability is critical. Accuracy too is critical, but let's just stick to stability right now. Okay, so to test stability or to figure out stability of a scheme for PD with finite difference scheme, we start with an exponential function. Okay, so my function phi x is e to the power x ikx ft. So ft is what will change with time, and we see whether ft is growing in time. For solutions, we should decrease in time. Okay, so let's see whether phi x is decreasing in time, but ft is growing in as function of time. Then we say the function is unstable. Okay, so that's the idea. So in some sense, the reminiscent of spectral method, where we had various Fourier modes, and we want to check whether the Fourier mode is increasing in time or not. Okay, that's the idea. Okay. Anyway, so in finite difference scheme also, we choose a basically a Fourier mode and see whether the Fourier mode amplitude is increasing at times when it should really decrease. That's the basic idea. Okay, so for diffusion equation, if we substitute this phi x, now it's discretized, of course. So we have it xi plus 1, xi plus 2, and so on. So xi is, or xj is j times h. Okay, so that's what we use. H is the distance between the two neighboring points. So j equal to 0, 1, 2. Hope I have nothing there. So it's very easy to substitute it here in the equation, in that Euler forward scheme, and look for the evolution of f. Okay, so it's function of time. So this is, what is it, at n plus 1, which will be n plus 1 here. Okay, so fn plus 1 is fn multiplied by a factor, which is 1 plus this object. Now, we had studied what about evolution, the KH before. When we computed the derivatives, we had seen that KH goes from 0 to pi. Okay, H is a minimum grid size. So K max will be, for Nyquist criteria, K times H is pi. K max times H is pi, this one. So here is the result. I had something here, but let's see. So even kh is pi, this becomes -2, -1, right? Kh is pi. So the worst case scenario, this is -1. Okay. Now I want to find what is the minimum delta t. Okay. So I want to make this prefactors to be the worst case scenario. Alpha should be largest. Okay. So this is -1, so that becomes -4. So this becomes -1 is -2 times 4. So this becomes 4. I'm using KHS. In fact, I'm using this to be 0. Okay, for this case, I'm using it to be 0. So this is being used. So this part I'm not considering. I'm considering only so the increasing part here, this part. I want to be in this range. Okay, so here I get 2k delta squared. So I want this whole thing to be less than 1. So that condition is 4 kappa delta t by squared is less than 1. Okay, this guy. Okay. So the condition by what we did in the past, this mod less than 1 is true only when this object is, well, 4 kappa delta t is less than 1. Okay, so basic condition is that this object should be less than 1. And I remember that, please remember that phi x is decreasing function. No, it's a diffusion equation. So phi x is in fact, later time is going like that. So phi x is, so f should decrease. All the amplitudes are going down. Okay. Finally, in fact, we get 0 as a solution if you wait for long enough time. So this is a condition for stability. So delta t finite difference is less than h squared by 4 kappa. Okay. So this is a condition for minimum delta t. Okay, h squared by 4 kappa. Now, if you look at spectral method, which we derived much before, is 2h squared by kappa pi squared. Okay, so this was done in the past for spectral method, and the ratio of the two is here. Delta t fd by delta t spectral. Sp is spectral. I just substitute. I keep here. Now I also use the condition that H spectral is a relation between H spectral and H finite difference. Okay, so I got here, yeah. So H spectral, H finite difference, FD is H spectral by 2 pi. Okay, this I had derived it while discussing the Fourier transform. For same accuracy, I would like this relation. Finite difference requires smaller h. Okay, for same accuracy or similar accuracy. So I take the ratio of the two and replace its h finite difference by uh, this. Okay, I want to cancel HSP. Okay, so that's what I have. HP squared divided by 2 pi squared. So the whole thing comes out to be 1 by 32. So this is telling us that my delta T for finite difference scheme must be smaller than delta T by spectral scheme by order 1 by 32. Okay, so I need a smaller delta T for finite difference scheme for the same accuracy. So it tells us that FD is more expensive. Well, Fourier transform also takes time, so it's another thing. But typically, you require extreme delta t and extreme h for finite difference, more resolution in finite difference. So I should not say more extreme, but you need more grid points and small delta t. Okay, let's say that. How much time is required for finite difference? That will depend on order of scheme, and of course, Fourier transform also takes time. So that part you can see. So more stringent delta T and H compared to a spectral. Okay. Now this is the solution from using FD method for same diffusion problem. We had a Gaussian. Exactly same thing what I did for spectral initial condition, and the exact one is the solid red, and the black dash is the numerical solution. Delta T is 0.001, and N is 64, and kappa is 1. And so both method looks roughly, I mean, okay, here there's slightly more error for finite difference, but we are doing okay.